Hey there everybody, this is the second video that I'm going to make on number sequences and that introductory activity that I had you do. Really quick, I'm just going to go back and remind you where we're at. We're here. The last video I didn't tell you what this is all about, and I want you to join me on a little journey with this as we go from here to my favorite number. I think told most of you, I think I told all my classes, and if you didn't hear me say it, maybe you saw it on the sign on my door, that I have a rather unusual favorite number. In fact, that's what I'm going to call this little presentation. I'm going to call it, I'm going to call it, I'm going to call it Y 13,532,385,396,179 is my favorite number. Yes, I'm reading it. I don't even actually have it memorized, but it's my favorite number. Why is it my favorite number? Well, join me and we're going to play a couple little games, and I'm going to tell you some stories, and I'm going to tell you why, you know, this number actually cost me $1,000 at one point. Because I almost won a prize, but I didn't, and somebody else claimed it. Ugh, it's a tragic tale. But it remains right now anyway my favorite number because it's got a really, really neat property to it. But first, we're going to play a game. And you've already seen this game. It is, in fact, the game that we left off on the other worksheet. What's the next number in this pattern? If I go 1, 1, 1, 2, 1, 1, 2, 1, 1, 1, 2, 3, 1, 1, 3, 1, 2, 2, 1, and that's the one I had a typo on when I first printed the sheet. And did anybody get there? Did anybody figure out what the next number in this pattern was? It's actually 1, 3, 2, 2, 3, 1. Did anybody get that? Hint. I first saw this pattern, I think in grade 7 or grade 8. I had the same teacher both years, so I don't remember which year it was. And he called it the see and say pattern. Do you know what a see and say is? This is a picture of a see and say. The see and say, you pull a little string on this, and the little thing spins, and if it lands here, it landed on A, it'll go apple, A. And get it? You see it and you say it. You see the letter, you see the word, and you say it. It's, you know, a little toy to help little kids learn how to spell and learn words and stuff. And see and say pattern, actually, it's very often called the look and say pattern too, but there's no toy called the look and say. So it's called the see and say pattern here. So there's the pattern. What comes after that? Pause the video if you want to try it for a minute. But here it is. Uh-oh. There we go. 2, 3, 2, 2, 2, 1. And then, if you want the next number after that, it's 1, 3, 4, 2, 2, 1. Interesting. It went down. Now I want you to think about something. What you'll notice so far is, and I think I pointed this out in class, notice even when the numbers get bigger than 1,000, like this one's technically, if you read it normally, it'd be in the 100,000s, it'd be 131,221. Notice I didn't put a space there or a comma. In fact, did you hear me calling this 1, 11, 21? No, I was clearly saying 1, 1, 1, 2, 1, 1, 2, 1, 1, 1, 2, 3, 1. Does that make sense what I'm talking about? Let me maybe go to a piece of paper real quick. 1, 1, 1. Where did I get this from? Because I looked at this line and what did I see? I saw 1, 1. Get it? I look and I see. I look and I say. It's a look and say. Whatever I see, I say. What do I see on this line? 2 1s. What do I see on this line? 1, 2, and 1, 1. What do I see on this line? 1, 2, and 3 1s. What do I see on this line? 1, 3, 1, 2, and 2 1s. Now at this point I've made a conscious decision. I've decided I'm going to say them. I'm going to look at the pattern, but I'm going to say them from the biggest numbers to the smallest. So that's why I put the 3 here first. 1, 3. So I'm looking at this 3. 1, 2. So 1, 3, that's this 3. 1, 2, that's this 2. And then 2 1s. That's this 1 and this 1. So that's the way I'm going to keep the pattern going. So 1, 3, 2 2s, and 1, 2, 3 1s. Now I've got 2 3s right there and right there, 2 2s, and 2 1s. And here's where the number 4 finally makes an appearance, because I have 1 3, but I have 1 2 3 4 2s and 1 1. That's why the pattern did that weird thing where it kind of looked like it went backwards. Okay. And, oh, it started it over. I didn't want it to do that. And that's why there. It went kind of looked like it went backwards, but it really didn't. So now, once my grade 7 teacher showed me that, like, again, nobody in class got it. I remember that. Nobody came up. But once they showed it to us, I was like, oh, cool. That's kind of a neat pattern. But then he did what I think is a really great thing that really stimulated my imagination when it came to this problem. He made it into an actual, don't just figure out the next line, but he made it into a reasoning problem. And he asked us a challenge. In which row will the digit 5 make its first appearance? So, in case you're, again, wondering, now, I don't know how I'm going to, maybe if I just do this. Does this do it? Yeah, there we go. If you look here, if we call this row 1, and this row 2, and this row 3, and this row 4, and this row 5, I don't see a 3 until row 5. And then 6, 7, 8. I don't see a 4 until row 9. So the problem is, in what row number will I finally see a digit 5 show up? So feel free to pause the video and keep the pattern going until you hit a 5. Okay? So I'll see you on the other side of that. Pause the video right now. What did you notice? Did you get there? Let me just pause something real quick here for a second. Sorry about that. Okay, so like I said, we are here. So your job was to keep the pattern going until you find a 5 and then tell me what number is. In fact, I think my teacher at the time offered a prize. I don't remember what it was. I don't know, soda or a chocolate bar or something. What row after row 9 will I finally hit the digit 5? I don't see a 4 until row 9. Where do I see a 5? And did you get that the answer is, drum roll please, never. If you did this right, if you followed the rules the way I put it through, I would have said to you, oh sorry, if you'd have actually done the rules the way I said it to you, let me go back to my piece of paper. You would have been at, okay, so we stopped here, 1 3 4 2 1 1. Okay, so let's keep the pattern going. So this was row 9, remember, right? So 1 4 1 3 1 2 and 3 1s. So this again was row 9. This is row 10. Now I have 1 4, 2 3s, 1 2, and 1 2 3 4 1s. We must be getting close to a 5. I've hit 2 4s. 2 4s, 1 3, 2 2s, and 1 2 3 1s. Okay, haven't hit that 5 yet, and I'm on row 12. Then it's 1 4, 1 2 3s, 1 2 3 2s, and 2 1s. Well, still haven't hit a 5, and I'm on row 13, so let's go to row 14. 1 4, 1 2 3s, 1 2 3 2s, and 1 2 1s. What happened? Well, guess what? Row 15 is going to be the same, and row 16 is going to be the same. Guess what? I'm never going to hit a 5. This thing loops on itself. This thing is its own next row. So when my teacher assigned that problem, he knew darn well that it was kind of a trick problem, that we'd never actually get there. And I remember this really impressing me. I would have thought this sequence would have gone on forever. It just kind of blew my mind that it'll actually kind of fold in on itself like that. So go back to young teenage or preteen me and ask what my favorite number was, and I'd have actually said 142332221, or I guess 14,233,221, because I was just so I thought that pattern was so cool that all of a sudden it just stopped and repeated itself. So That was my favorite number for a while, which means that I wanted to put it on a jersey, but it was too big. So the look and say sequence also has another name. It's also called the Morris number sequence. And to be honest, I found out years later that's actually not really the way to play the look and see sequence. The actual look and say sequence actually does go on forever. You can watch a video on it. This particular problem, and I mentioned this in class, stumped maybe the greatest mathematician of our lifetime. We lost him to COVID just about a month or so ago. His name was John Conway, and yeah, it makes me sad just to find out that he's gone. But Numberphile, a YouTube channel that I just absolutely love, has many, like a whole playlist of videos of John Conway. He really was a brilliant man. And this is his video on look and say numbers. I'll put a link to it at the bottom of the description. And he's quite upfront about the fact that he did not get it. But once he got the pattern, once somebody explained it to him, he did, like everything else he touched in mathematics, he did some wonderful, marvelous things with it. And if you watch the video, you'll see that actually the way we played the game just now isn't exactly the way that you're supposed to play the game. If you play the game the right way, it actually is an infinite pattern. But, interestingly enough, not only will you not hit a 5, if you play it the right way, you'll never go past 3. You won't hit the number 4 either. So, watch the video and you'll see that. Oh yeah, there we go. We have a whole channel dedicated to John Conway of a whole bunch of videos he did, and the look and say numbers is one of them. Now we're going to play another game. So, does everybody remember how to make factor trees? I'll do one real quick, just to see if you remember how factor trees work. So let me get to my piece of paper here. So let's make a factor tree for the number, I don't know, 24. That's a nice number. So let's see. Well, 24 is 2 times 12. I could have also put 8 and 3 or 4 and 6, but I'm going to get the same answer at the end anyway. 12 is 2 and 6. 6 is 2 and 3. And there we go. I have a factor tree that has finished. Now, I never break down 2 into 1 times 2 because 1 is not a prime number, so it doesn't belong in the factor tree. Every branch ends at a prime number. And if I rewrite it from smallest to biggest, I have what is known as the unique prime factor number sentence that will give me 24. Every number has its own unique prime number generating multiplication. Prime number factorization is what I'd call that. So obviously now you remember that if you did the assignment I gave you on EDSB, you were supposed to tell me your favorite non-prime number. Some people goofed up and they accidentally said, oh, 17. Well, wait a minute. That's make a factor tree for 17. Done. That wasn't very exciting. So that's why I didn't want any prime numbers. But if you'd have picked 18, well, then you had 2 and a 9 and a 3 and a 3, and you'd have had 2 times 3 times 3. So take your particular non-perfect or non-prime favorite number and make a quick factor tree out of it. But do one more thing. This is maybe the way you left factor trees in grade 10. Here, let's just, if you have repeating factors, can you exponentiate them? In other words, turn them into exponents. So there we go. If your favorite number happened to be 24, and I think a couple people did, that would be your answer. If your favorite number was 18, that would be your answer. Stop the video. Remember what your favorite number was, non-prime number. Obviously, there was a couple people picked 0 and 1. Can't have those. Yes, you're right. They're not prime, but you can't make factor trees out of 0 and 1. So pick a number you can make a factor tree out of. Make a factor tree. Turn it into an exponential prime number factorization. You always have to go from the smallest factor to the biggest. Pause the video and do that with your favorite number, and I'll join you back in a second, okay? So give that a try. Okay, we back? Did you try it? So 24 is 2 times 2 times 3. Now, here's what you're going to do. You're going to take your answer of 2 to the 3 times 3, and you're going to remove all the operations and treat the exponents as if they were normal digits in the usual base 10 way. In other words, turn this into, okay, first you turned it into an exponent, right? Then turn the exponent statement into just 233. Because, get it? 2, 3, 3 is now the number 233. Now, ask yourself if you can make a factor tree out of this. Can you? Well, if you can, then you make a factor tree and repeat the process. If you can't, your game is over because you've hit a prime. This game is called Climb to a Prime. So, I'll get to that in a sec. So, the Climb to a Prime. So, we just did it with 24. Let's do it with the other example I had. Let's do it with, what was it? It was 18. So, 18 gave us 2, 3 to the 2. So, 18 gave us 2 times 3 squared. So, ignore the operation, ignore the fact that that's an exponent, and make that the number 232. Okay? Now, can I make a factor tree out of that? Now, obviously I can because it's even, so it's got a 2 in it. So that's a 1, and 2 goes into 3. Once carry the 1, so it's 116. And that's also factorable because it's got a 2 in it. So 2 goes into 11 5 times with 1, so 58. That's also factorable. It's got a 2 in it. So that's 2, and 2 goes into 5 twice with 1 left over, 29. I'm done. 29 is a prime number. So this is 2 times 2 times 2 times 29. That is the prime factorization of that number, of the number 18. And I am now going to put all that together as 2 to the 3 times 29. And then I'm going to turn it into just a new number, 2329, and ask myself, is that prime? Now, here's where the game gets kind of tough. How do you know if that's a prime number? I mean, you could go, well, does 3 go into it? 9, 10, 11, 12, 13, 14, 15, 16. No, 3 doesn't go into it. Does 7 go into it? Remember, there's no quick trick to figure out if 7 is a factor of a number. You have to actually just divide by 7. This is already getting to be a total drag. I have a solution. Let's go to my Google page and go to the prime number calculator at math.com. I'll put a link to this at the bottom of the video, and let's just ask the computer, hey computer, is 2,329 a prime number? Is it prime? Ooh, it's got a 17 in it. All right, well, fine. So then I'm going to go to my calculator, and I'm going to go, okay, make a new factor tree. So 2329 is 17 times something. So I'm going to use my calculator to help me here. 2329 divided by 17 is 137. You know, I don't even know if that's prime. 10, 11, it doesn't have a 3 in it. Let's see if it's prime. Let's go back to the website. Website. Is 137 a prime number? I think it is. Yes. So I'm going to go back and make my new number. This number is 17 times 137. No exponents involved this time. Make that one number. Get rid of the times and make it one number. Is that a prime? 10, 11, 18, 19. It doesn't have a 3. But I don't know. Is that a prime number? Did we climb to a prime? Let's ask the computer. Computer, is 17,137 a prime number? It is. So the game is over. We have climbed to a prime. Remember the first example we did was 24? 24, this one took several steps. 24 only took one step, right? 24 was 2 to the 3 times 3, which is 233, and 233 is a prime. In one step, we got a prime. This one took, 3 steps to get to a prime. Well, how did your favorite number do? Was anybody's favorite number 8, which is 2 cubed? One step. Was anybody's favorite number 9? 9 is 3 squared, which is 2 to the 5, which is 5 squared, which has a factor tree of 2 and 26, which is 2 and 13. So that's a new number of 2 squared times 13. Is 2213 a prime? Let's see. Well, let's see. Does 3 go into it? 3, 4, 5, 6, 7, 8. No, it doesn't have a 3. I think I'm going to check with the computer. I think my hand just froze too. Oh no, there we go. So, computer, is 12,213 a prime number? It is! So we climbed to a prime. Isn't it interesting that 24 only took one step, and that's a bigger number than 9, whereas 9 took a while. I picked 9 because a whole bunch of you had 9 as a favorite number. And it climbed to a prime in 1, 2, 3, 4 steps. Now, did anybody have as their favorite number? I think somebody did. If I remember going through your homework, did anybody have 20 as their favorite number? Because you know how many steps it takes to get to a prime? Neither do I. They've used computers and they've done hundreds of steps until the numbers get so big that even modern computers can't figure out if those are prime numbers or not, and they give up. We have not got evidence that the number 20 climbs to a prime, but we don't know that it doesn't. So that is where John Conway comes in. John Conway made the conjecture that every natural number will climb to a prime the way that we've just been playing, and he offered a $1,000 prize to anybody who could prove or disprove it. Just for a couple more examples, 90 climbs to a prime in 3 steps. 80 takes 12 steps, and you finally hit a prime that is, let's see, what is that number? 3,383,253,442,213. But that number is, and a computer can check it, truly prime. 20, they've done over 100, over 100 steps. I actually think it's a few hundred steps. And you end up getting prime so big. Look, at a 12 step gets you to a trillion. So think about how big the prime numbers would be after 100 steps. And we've still not, we don't know. But again, we don't know that it doesn't. So John Conway offered $1,000. Can you prove that every number will, if you play this game, climb to a prime? Or can you prove that there is at least one number that doesn't? And I heard about John Conway's 5 unsolved problems, that the prize for each of them was $1,000 if anybody could solve them. As of right now, I think he put this out in the early 1980s, these 5 challenge problems. And I think only 2 of them have been solved, and this is one of them. And I thought I could solve it. When I was a young guy in university, I heard about this problem, and I thought it was neat. And you know what it reminded me of? It reminded me of the look and say, or the see and say problems. This is what I thought. Since numbers are infinite, it made sense to me that there might be a number that is its own prime factorization. It made sense to me that the piece of paper I just put down isn't here. There we go. It made sense to me, sorry, I'm a little disorganized here, that it might be like this. There might be a prime number that's so long that let me put it this way. There might be a number, not a prime number. There might be a composite number so long, a non-prime number, that when you make its prime factorization statement, you make itself and you get stuck in a loop. I thought that would be the case. I wasn't the only guy that thought that way. I got a friend of mine who was a computer scientist at the time on a very crappy early 90s computer that, everybody here has a phone far more powerful than that thing. I think it was a 386 megahertz Pentium. We wrote a program checking numbers to see if when you factorize them that you would get itself. And I never found it. I guess my program that my friend wrote didn't quite work. I thought we had checked numbers bigger than this, but that gets me to my favorite number. This is actually something I knew too. This is kind of cool. I forgot to mention this. Notice that 2 to the 5 times 9 to the 2 is 2592. Now, obviously, these are not prime factors because 9 is not a prime factor. But again, I knew that the possibility existed that a multiplication statement could equal itself. Why couldn't that work with this being a prime number and this thing being the same digits as that thing? Turns out I was right, but I wasn't the one who found it. About 5 or 6 years ago, I think, a amateur mathematician but a professional physicist found this number. And here's what's so beautiful about this number. This is why it's my favorite number right now. This number, if you made a factor tree for it, you would get 13 times 53 times 53 times 3,853 times 96,197. In other words, put this all together in the climb to the prime way, get rid of the multiplies, turn that 2 into just a digit, and this prime factorization is itself. And this guy won the $1,000 that 35 years ago, I thought I'd be the guy to win this money. But no, James Davis beat me. But what's really amazing is that I don't think his program was all that more sophisticated than mine. Essentially, he took a lucky guess Essentially, he narrowed his search for numbers to a certain field in the trillions here, and I think he might have had a bit of luck on his side, and he stumbled on the answer. To this day, nobody's found another one that behaves this way, at least not in base 10 numbers. And this is it. This is the climb to the prime solution that won $1,000 that, by golly, should have been rightfully mine. Anyway, that's the end of my little slideshow. And thanks for playing along. And for those of you who I put a note on your assignment, hey, that's an interesting favorite non-prime number. Is there a story behind it? I'd love to hear your story sometime. Some of you had favorite non-prime numbers in the hundreds and in the thousands. Tell me why those are your favorite numbers. Is it as weird and long and strange a story as why this is now my favorite number? Thanks for watching, everybody. We'll call that a video.